I'm going to go ahead and get started here. Just the usual reminders. So we are working on decision trees and ensembles. This unit 11 this week was on the chapter on decision trees. Then there's a separate chapter from our textbook on ensembles. So I'm going to start off. We do have a assignment 5 basically over the ensembles, decision trees and ensembles. I'm going to start by looking at that, and then we'll see if anybody has any questions or anything, and then we'll go back and finish up the notebook that we started looking at on decision trees. I haven't had a chance to check. I know some people are working on it, so presumably the assignment invitation and everything is working here, but I haven't actually accept it myself yet, so let me go ahead and accept this and do the usual to get it cloned and get started on it here. So, actually I meant to also mention before I get started on that, Martin. I was just getting started. I was planning on kind of starting up with assignment 5, bring that up, just make certain, see if anybody has any questions on it. Just look over it. We still have this week, we still have another week, a week from tomorrow for the assignment 5. It is on decision trees and ensembles. So we'll also go into some details on it next week. There's some stuff that the last part of the assignment 5 is really some stuff about kind of building some ensembles by hand. So I'll probably leave going into some more details on that till next week. But yeah, before I jump into that, I did want to just remind about the class project again. So we are getting up to the last 4 or 5 weeks here, so there's not that much more time. I've been kind of busy. I'm still working on getting back the assignment 4 people, so look for that. I'll try and get that. If I get a chance, I was gonna maybe do a little bit of feedback on your class project as well. Just maybe make a little checklist, see if people have been making commits, see if I have any questions or things on what people have worked on so far. So. I'll try and do that. Look for that maybe before our next meeting next week sometime as well. So yeah, if you haven't been thinking about the class project, been doing some work on it, made some commits yet, it's kind of a reminder that it would be better in terms of your evaluation and other stuff if you're working on it each week a little bit. So doing some incremental work, thinking about it more than just kind of a last minute sort of thing. So. Okay, yes, like I said, I was just going to maybe bring up the assignment 5 first real quickly, just to discuss some things about that. I haven't actually cloned it yet personally, so let me go ahead and clone it in here into my repos directory and get it reopened in container so I can open up my notebook. So, since I haven't done this, it might take a little bit of time here. So, while the container's building here, I'll jump back to look at it on GitHub, the notebook on GitHub here. So, all right. Let's see here. Let me remind myself how many tasks there are. So in total, it's defined as 5 tasks, six tasks. So kind of reminder on that, you really should, at a minimum, have a commit for each one of the tasks. So, I might ask you to redo some stuff if you're not showing me the progress of the work as you're doing the stuff in the assignment. We do have the same format as you should be familiar with right now. So there's a few of these. You have to implement a function in the source assignment task directory. So some of them, the first one should be kind of a warm-up. That is just to load the data. A little bit about this data set. This is a little bit, we haven't talked about this one, looked at this one before. This is a data set from, I believe it was like a Kaggle competition or something like that. So it's a bit of a synthetic data set, but it's relatively complex. So what? There's a little under 20,000, I think, samples in this. It is a binary classification task. So you don't have to know too much about it, although it certainly wouldn't hurt for the assignment to at least read kind of the data description, the data dictionary, a little bit about it. So. Yeah, I did ask you to use the fetch OpenML. So the scikit-learn kind of has some hooks in here to get different data sets that are used commonly for doing things. So this one is one of those. So you might have to read the documentation on the fetch OpenML to figure out the parameters that you use for that. But yeah, so yeah, don't download the CSV file by hand. Do go ahead and use the fetch OpenML to get that in. So hopefully that won't be. Hopefully that won't be too much of a problem for most people. So the data set is a classification problem. It's a little bit skewed, so it's actually about 2/3 of the data are the positive G class. So you should use one. So I think one of the tasks is you do have to encode this a little bit. So I do ask you to do a train test split. And in here, actually maybe on the first task you do have to encode. I can't remember if it was the first or the second task, but yeah, you should be. You probably won't be able to pass the test unless you correctly encode the G class as your ones, the positive class, and the H class as the zeros, the negative class there. Okay. So yeah, I don't know if I've discussed this before, but when you're doing a classification, if the data is skewed, so if the label, the target you're trying to build a model of is skewed, that makes the task a bit more difficult. Okay, so this you can get some that are really badly skewed. So you might have something where if you're a binary classification class where 90% or even more is one class. So those can be especially difficult because you don't have as many examples of the negative class. So sometimes you have to do special things. You have to oversample the class that's not as representative when you have big skews, of course. Same goes for a multi-class classification problem. So anytime you're trying to fit a set of data for a classification task and you don't have a roughly equal breakdown of all the classes, you sometimes have to maybe do something about that. So that might be relevant to some people's class project. So keep that in mind. If you picked a data set that's a classification task, and even if it's as kind of a little bit of a skew like this, 2/3 are one of the labels and 1/3 is the other label. You might want to explore things like oversampling or artificially generating samples in order to get the data that you train with a little bit more even. So we're not going to do that on this assignment. I just was thinking about that a little bit. I don't think we've really discussed that in the class before. So yeah, for the task one, you do need to just make this function that will load it. You do have to do the code encoding correctly, so you might want to use one of the scikit-learn's encoders. Although this data is simple enough, you could do it by hand, but I didn't really specify. But but you can use like an ordinal encoder or something like that in order to get what's asked for here. And this is supposed to return back, the data set. So I think there's like 10 features or so. All the features are numeric. And then, of course, our binary label, the G or the H. Yeah, and in this one, it is important that we split the data. So for especially for the final task on the assignment 5, where we kind of build an ensemble by hand, we're going to have to do it in stages. So like I said, I don't think I'll go into too much details on this today. I'll leave that till next week, unless people have some questions on it. But I'll just mention that. So one of the purposes of the task 2, we haven't had a lot in our assignments where we had like a 3-way split, like a validation test set. So we do really kind of need that for this assignment here. And again, the second task is there's no function that's part of scikit library that will do a 3-way split, give you a train validation test. So so this one is just again a little bit of practice on using scikit-learn library and writing regular Python code, regular Python functions. So the idea is to use the basic scikit-learn train test split function to make a 3-way split. So we have kind of a convenience function that's a wrapper around calling the train test split twice. So, but again, I am expecting the result from this when we do the unit tests that you split it the way that is mentioned here. And for this one, we had an issue with this before, so I think as is described here, you do need to set the random seed when you call the train test split for both calls inside of your implementation in order to pass the unit test that I give for this. So it's expecting that seed is 42 and that you're calling scikit-learn's train test split twice in order to get the expected split and the expected values in each of the 3 sets. But yeah, so you need to have this function working. We are going to be using the train validation and test sets for the rest of the task for the assignment. So this function will be reused by you or by the tests. Actually, both of the first 2 functions, to get the data and to split it in the expected way when we're building and testing our ensembles. Okay, and yeah, I forgot. So I'm not going to talk about actually ensembles today. We're going to finish up on decision trees. So really, the rest of the stuff is about creating ensemble classifiers. So one of the classifiers you're supposed to use for task 3 is a decision tree, but you're supposed to also basically create 5 separate classifiers. So k-nearest neighbors, we talked about all of these except for multi-layer perceptron. So if you're not familiar with that, that's really a neural network, like it says here. So kind of a pitch, we will have like a neural networks class this summer, or if there's enough interest in it this fall or thing. So it's really a neural networks and deep learning class. So there's kind of some hot stuff. So if you're interested in that, let me know, so I can kind of gauge whether we need to try and get it on the books for spring, and whether we're going to be able to do it this summer or not. So it's a very logical course as a follow-up for machine learning. So the background that you learn on the machine learning, especially using like the scikit-learn library, is good then for understanding how you do neural networks and deep networks and things like that. So anyway, so the MLP, multi-layer perceptron, is really just a fancy name for a basic feed-forward neural network. But all of these are, from the scikit-learn library, so they should all have pretty similar. When you build these by hand, you have to create an instance of each of these 5 classifiers in your task 3 function so that you have separate classifiers, and then you have to use the scikit-learn ensemble class to combine the results of the separate classifiers into a single classifier. That's really what an ensemble is having multiple individual classifiers and then combining their results in order to hopefully build a classifier that actually works better than any individual one does at predicting on your data set. So yeah, I think there's two functions. So you're supposed to, you're supposed to just write one function for task 3. There's a parameter though, so I won't. We'll talk about hard versus soft voting ensemble. So you're supposed to first try it as a hard voting ensemble, and then just do it as a soft. I don't think there's anything you have to do for the second test here, as long as you implement it correctly, that you're using that parameter to either have your ensemble be either hard or soft voting. So. Okay, so yeah, we will go into more details on all these things. So the stuff starting on this, well, actually, really the task I've already been talking about is really the ensemble materials for the most part. That's in the chapter that we're mostly focusing on next week. So the most common kind of ensemble is really a random forest or an extra trees. So task 4 is, if you've done the readings or when you do the readings about ensembles, we create, the textbook creates a random forest by hand so a random forest is really just a large number of decision trees that you combine together in an ensemble to make a classifier, okay? And an extremely random forest, which is what the extra trees is just also a random forest with where you do some slightly different things in the way that you create the individual decision trees. Okay? So really task 4 is about creating a random forest by hand by creating some multiple decision trees and then using the scikit-learn ensemble. So, yes, I might be saying something a little bit wrong on that. So yeah, actually, task 4, you're supposed to really just not do it by hand, but just use a random forest or a extra trees, your choice. And then there's some description of some other stuff. We'll talk about the bagging and pasting stuff. That's all in the next lecture notebook after this one and the next week's chapter. So 5 and 6, I'll just kind of be brief on this. We'll go into more details of this. 5 and 6 might be the ones that most people will need to spend the most time on this assignment. So if you haven't started, if you haven't started on assignment 5 as usual, I encourage you to, I probably don't want to wait till the day or two before it's done. You should probably get started on it this week. If anybody's watching this hasn't done that yet. So 5 and 6 might take the most time for most people. So what we're really doing on 5 and 6 is building an ensemble. The idea of the stacking that's talked about here, just to give a kind of a summary on that, is so the basic voting ensemble, all we do is like it's like a vote. So if we have 5 classifiers, and if we're doing a binary classification, whichever of the class is the most highly predicted, right? So 3 out of 5 or above. For a binary classifier, it's easy to understand the voting a voting ensemble because one or the other has to have more of the individual ensembles that made the prediction for either one of the class or the other. So whichever has the largest, that's really what the hard voting is just the majority vote. So doing the stacking, when you read about this, if you haven't done the readings next week yet, we have multiple classifiers that we're going to combine together into an ensemble, but we do something a little bit more sophisticated than just doing like a straightforward vote. So really what you do is you build another classifier that takes the inputs of the individual class, that takes the individual classifier's outputs and our inputs to another model that you build in order to combine together an ensemble of the individual classifier. So that's really what the stacking idea is we're building a new classifier that takes the outputs of individually trained classifiers as inputs and does something more sophisticated than a vote. Okay. So 5 and 6 are support in order to do that. So 5 is really a way in order to, what you're going to be using the create stack data for is this will allow you to input the outputs of some classifiers and combine them into a data set that can be used as input to train another one, the stacked classifier. So we'll talk more details about that next week once we get into talking about ensembles, and then the last part, the stacking and those kinds of issues. All right, so let me know if people have questions on that. You can email me or whatever. Oh, by the way, there's something happening today, so it might not be in office hours. Or if I am, it'll be near the end of them. So let me know, email me if people were hoping to catch me today. So okay, so yeah, actually I never did use my VS Code here, but yeah, I've got my container finally was done. But let's go and move on. Okay, so for the rest of the time, we had a couple more things to talk about at the end for the decision trees material. So let's just finish that up. Check something first here real quick. Okay. Reopen our class materials. Okay, so just kind of a quick summary of a couple of things from last time. You probably don't have to understand all the details of how this works, but it is a good idea if you want to use decision trees well to understand the idea of this Gini or other kind of function for measuring how pure or impure. So Jenny uses the term purity. You can use other functions as well here for a similar idea, right? So based on that measure, that's really what is used for the cart as the fitness function. Okay, so if you understood the ideas about optimization and gradient descent, we're doing something, basically the same idea here. So the fitness function that's used for the decision tree training algorithm is really using the Gini in order to define a fitness function. And basically, the better that your split is, the lower that the cost J is going to be. So the better the split is for some parameter at some threshold for that parameter, the lower the cost will be. So once you define that, you can actually use the same kinds of optimization methods that we did, with the difference being, though, that this isn't optimizing over the whole classifier. This is greedy. Okay, so that's another thing that's good to understand. Although in practice, when you build a decision tree in scikit-learn or like a random forest or something, it doesn't really affect you too much, because the greedy algorithm is usually going to come up with a resulting tree that would be close to what you would get if you could optimize over the whole tree at once. So, but yeah, for performance reasons, it ends up actually being an NP-complete problem to try and define a global kind of cost function for this. So we have to do a greedy version of this, where basically at each node, the tree is built incrementally. So we start for the root of the tree and find the best parameter and threshold to split that, and then we just keep doing that until we can no longer split. Another thing before I move on to some new stuff that's good to know is the basic decision tree. If you don't constrain it, it will always end up building a decision tree that will give you perfect performance on the data that you train it with. So we got into this a little bit last time, but we were constraining this tree to have a depth of 3 when we did it before. So when we a depth of 2. I'm trying to remember. So by definition, we include each. This one is including each level below the root node as the depth. So it's a depth of 0, would only have a root node. You probably can't specify a depth of 0. It's not making any decision at that point. So you have to have at least a depth of 1 or bigger. So a tree like this is a depth of 2 here. But if you don't specify a regularization parameter like depth, there's other regularization parameters that you can specify. Maybe I'll talk about those later. But if it's unconstrained, it will just keep splitting and splitting until it gets down to a Gini of 0, to a perfect a node that has perfect no impurity, basically. And what that looks like, if you visualize it, is you just get more and more splits until all of the leaf nodes at the bottom of your decision tree have only one class in it. Okay? Which means that in practice, that if you ask it to make predictions on the data you train with and you haven't constrained the decision tree, it'll make perfect predictions. It'll have 100% accuracy, right? But you can't do that with like if you do use no regularization on a basic logistic regression or support vector machine, unless the data is linearly separable, you won't be able to get a classifier that will get perfect performance on the data that you train with. Right? But you can't always do that with the decision tree, because it's not making one decision boundary. It's splitting and resplitting the data as far as you ask it to. So all that is by way of saying that yet the kind of the default behavior of using a basic decision tree is it will always overfit badly. So it'll always give you a resulting classifier that gives perfect performance on the data set you build the decision tree with using the CART algorithm, but that's likely to not perform well. All the problems with overfitting that we've talked about before. It's likely not to perform well on predicting unseen data if you let it do that. So you usually do have to do something to regularize the decision tree. And the basic regularizations, I should have reran this, but let me rerun this while I'm thinking about it here. So, oops, died. So, I just wanted to bring up the help for this. So, max depth is often the one that's most used as kind of a regularization for decision tree, regularization parameter, but most all the rest of these meta parameters for the decision tree classifier also can work as regularization functions. So so for example, I'll just pick one or two of these. Specifying the max leaf nodes kind of indirectly can limit the depth, right? So like in our tree that we had here, it had 3 leaf nodes. So if we had said max leaf nodes 3, we'd probably gotten the same decision tree as using a max depth of 2. So a bit indirectly. The difference being that you don't know how balanced the tree might end up being, like this one, since we end up with a perfect no impurity for our first split there. We can't split that one any further, so any other growth of the tree has to happen on the right branch from the root there, so it's going to be pretty unbalanced in that sense. Right? So so you can specify, for example, that you should stop splitting if the impurity doesn't decrease by some amount, right? So if the best it can find only makes a really small improvement, then it wouldn't actually do the split, right? So again, that would stop it from going all the way down to where you end up with a pure, a zero Gini measure here. So later on, when we talk about on the ensembles, the bagging and those kinds of concepts here. So one of the things that we do when we build an ensemble using decision trees is we want the decision trees to be different from one another, okay? So one way that you can do that is you can say, like for example, for the assignment that we're working on, we've got 10 features in that Magic Telescope data set. So you can say, like if I'm building a random forest, build trees that at most only use 2 of the features or 3 of the features. That's kind of what max features is doing here. Although this is while it's building the tree, this is kind of, I think it just picks some number of features at random and finds the best split among the features that it picked at random. At each thing, and then iteratively at each node it does that again, picks another. So if you say only consider 5 features, and I've got 10 features like the Magic Telescope data, it would only consider 5 at random, pick the best split it can among those 5, and then it would pick another set of random features, right? So that way, this adds some randomness in there. So like. If you don't specify something like that, you should get pretty much the same decision tree because the best split, like that, for example, here at the root, since it's linearly separable, the setosa is to pick that parameter and the threshold for that parameter, the pedal length at 2.45 should give you pretty much the best that you could do for the first split in terms of the weighted average of your Gini impurity. So, anyway, it's good. I don't know. In practice, for myself and personally, usually, maybe if I'm doing like a grid search, besides max depth, I might try 2 or 3 others in a grid search. But often, just one of them will give similar results in terms of regularizing your resulting classifier, so that it doesn't, isn't overfit on the data. But there's a couple of different ones you can use. So I guess just to summarize on that, the things that you use for regularization on decision trees are those, and they have the purpose is similar to what we've talked about, like for the regularization parameter that we use for logistic regression support vector machine, where we only had really the one, but here we've got multiple ones that you can use to try and fight overfitting. So yeah, I just mentioned again. So really, the trying to optimize over the whole decision tree is known to be a NP complete problem. So if you know what that means basically it grows exponentially. So it's impractical for anything but trivial data sets to actually set it up to optimize to find the very best tree overall. So the greedy algorithm, though, has a complexity of something like that, which means it only grows in the size of the number of features, the number of samples, or the number and the number of features. So much more reasonable. So even really large data sets, you can build decision trees on in a reasonable amount of time. And also, maybe I'll skip over this mostly. So, we mostly talked about Gini impurity. I was trying to remember. So entropy is another common concept, but it gives a similar idea to purity of a split. So you can use this. There's probably other functions that you could use besides Gini and impurity, but I think scikit-learn only supports those two. Again, also for me in practice, if you're playing around with decision trees, think they might be really useful for something, I usually don't find a whole lot of difference. So I've never had a data set where you got a large improvement over picking entropy over Gini. They're usually pretty similar. So I'm sure that there probably are some problems where it might be, you might get big improvements of switching over to entropy, but I'm not certain what they might be that would cause that. So. But anyway, so it is good to know kind of that can be used. So. Shoot, I forgot. Yeah, so I'd been talking about this. So there was a section on our notebook about regularization as well. We talked about max depth. So these were some of the other, probably what our textbook discussed a little bit about these. So min samples per split, min samples per leaf, max leaf nodes, I mentioned a little bit, max features. Here's some examples if you haven't done the readings on the textbook or looked through this notebook yet. You can get a little bit of a better feel here. In this first example, the Moons database, maybe a little bit tough to see here, but remember this just is a way, it's a function that generates an artificial data set that's has a nonlinear decision boundary. So the decision boundary is probably something like this here with some noise. So even a little bit tougher than that to do. So you can kind of see, so for people watching the video here, the decision boundary is something like what I'm tracing out here with the mouse. And so here, we did, in this first one, we didn't specify any of those regularization parameters at all. So you get a lot of splits in order so that it can have leaf nodes, even if it has to get down to like 1. So probably, for example, this one right here was a split in order to get this one out of all the others. That looks like it might be a bit of an outlier, some noisy data that was made from the moon's function. Same with this one over here. So it'll get a bit messy, So I should have, would have been maybe a good idea to add in some examples. So when we do this one here, since we didn't specify any regularization by changing the max depth or something like that, what you would see would have been a good idea for me to demonstrate this in the notebook. Is, for example, if you ask it to make predictions on the training data, you would see it's 100%. It makes perfect predictions on data you're trained with. But here, when you limit it a bit, so here again, there's some kind of things that end up specifically when we limit the depth to 4. You'll see some jaggedness, some attempts to pull out some stuff on this decision boundary, but it's much less than the one before. So this one here, where we regularized, won't get perfect performance on the training data, but if we were to split the moon's data, and then it would probably perform quite a bit better than the first one on a test data set. We split it out. Oops, that's okay. Okay, and kind of the final thing, still got 10 or 15 more minutes, but you can actually use decision trees for creating a regressor predictor. Just have a classifier. So yeah, kind of at first glance, it seems more natural the way decision trees work as for building classifiers. The idea, if you want to use it for a regressor, is this is described here. So if you want to use it for regression, we're going to be using a similar cost function, but we want to do it in a way that splits the mean squared error, like we used for regression problems before. That same idea, right? So the result of that, so you'd use kind of the same cost function and the same CART algorithm that we discussed before, but instead of Gini, we would just use MSE. And if you think about it, the reason why that works is, for example, the first one that it would get would end up being the line that ends up being basically at the median, right? So the one that splits the top half from the bottom half. And then from there, if you continue splitting on, these will be for subportions of the data set. Well, I guess that a little bit more, a better way of thinking about it is, so what would happen is if we split it and using the mean squared error, it actually ends up kind of dividing it up into sections. So basically everything, so here this was, again, this was like a quadratic function with some noise on it. So we ended up with decision nodes and decision tree that we're splitting based on this feature being less than, a little bit below 0.2, and another one being a little bit less than like 0.7 here. So for that first one, if it was below 0.7, it might have had so yeah, in this case, right, the prediction, the output is going to be, a real valued number instead of one of the classes, right? So when we also, some differences when we do the using the mean squared error, we're still using the CART algorithm, but if I were to go back and look at the tree here, the resulting split would be really what the predicted output level is instead of the split of our classes. Right? So approximately like 0.3 here for the split that we did, or I guess I was looking at this one here. So it's useful, if you want to try the decision trees out for doing regression to see what happens if you, again, if you don't regularize the tree. So what happens is that you end up getting more and more leaf nodes, and you end up splitting up into much smaller and smaller segments, right? Until you get down to you're splitting every point into an individual segment that will predict that one. But again, this is probably overfit again, so it's fitting the noise rather than the true function, which is probably a smooth curve on this case here. So you can use the same regularization parameters for regression. So this might be underfit a little bit. This is probably definitely overfit. So probably something somewhere in between that would be give you a better performance on your test data. Okay, yeah, so I'll just wrap up that. I don't think decision trees are particularly used very often for regression, but they are more natural kind of thing. As classifiers because of the way they work. They can be used that way, but I tend not to use them for regression problems. So. Yeah, and there's a couple of other things that are good to know about. It's kind of the very end of the chapter on decision trees from our textbook. The decision boundaries that are made are always orthogonal, like I said, so always at right angles to the feature space. So that can be unnatural for certain data sets. So something that, I wish I would have brought up the textbook here to show that figure. See if I can get it real quickly here. So when it talks about the sensitivity to axis rotation, this was the figure I should probably put in the lecture notebooks that I had. So here, the decision boundary, which would be easily found by support vector machine or a linear regression or a linear support vector machine, is at a non-90 degree angle to our two features, our two-dimensional data space here. Right? So so decision tree, if the decision boundary is orthogonal to one of the features, it'll do just as well as like linear regression, but it would be kind of have to do multiple splits and multiple leaf nodes in order to get something approximating what might be like a straight line, just not at a right angle to either of the features. So what that means, though, then is that we haven't talked about principal component analysis, so I'll mention that as well. So after we're done with ensembles and decision trees, we are going to get into unsupervised learning. So we'll talk a little bit about principal component analysis and also some other methods on that. So principal component analysis is a way to scale and kind of rotate the data. So presumably you can end up getting some performance gains if you're looking at decision trees, or maybe also ensembles of trees by doing a little bit of PCA on the data and fitting your classifiers to the transformed data set. So yeah, some other kind of sensitivities. So small changes in the trained data set. So the basic decision tree is kind of deterministic. So it should be making fundamentally the same split at each decision node, unless you specify some of the parameters that cause it to put some randomness in there. So that means that you can get things that look very different. If your train test split is done using like a different seed or something like that, so you can get kind of jumps in performance and things, which can make it hard to understand. What is the best parameters and things for decision tree. So anytime you have stuff happening like that, it just kind of hides. And makes it more difficult to understand, what would be the best settings to get kind of the best performance on my predictions. So. Okay, yep. So that's pretty much it. That's the basic stuff for the decision tree. So I'll go ahead and stop there for today. Yeah. So I already mentioned. Let me know if people have questions on the assignment. Make certain that you're working on that. If you haven't started on it yet, it'd be a good idea to start on it before the end of this week here. And we will finish up, we'll get into the ensembles and get into more details of the last tasks next week on Tuesday and Thursday. All right. That's it.